right, thanks, Heather. So, thanks a lot for the opportunity to speak at the University of British Columbia Library School. I'd like to talk to you about open notebook science and the implications for the future of searching and the future of what libraries will actually do. So, first slide, talking about open and closed science. So, this is just a general overview of some of the trends that are happening currently in scholarly research. We're going from a situation both in research and teaching, which has been traditionally very closed. So, in research, we have the traditional lab notebook, which basically is unpublished. No one gets to see that notebook except for the student, their supervisor, and maybe a few immediate colleagues, but it's certainly never made totally public. So moving more towards the open, we've got the traditional journal article. So that's what most of us are familiar with. It is a collection of data and a collection of conclusions and opinions about the data that are put into sort of a standard representation. This standard representation is then sent off to a publisher, and if it's accepted through the peer review process, it'll show up as an article that can be cited. So this is more open in the sense that anyone in the world can access the article, but it's still not as open as it can be because typically, you have to pay for it. And so taking this one step more towards the open, we have open access journal articles, and I think you've had at least one speaker in your class on that, and certainly that is a very exciting trend where it's actually either the author or some third party who's paying for the cost of publication, and the articles are made available free to anyone in the world. So of course that's more open than a traditional journal article, but it still has the same format as a standard article. And the problem with that is that articles don't actually cover most of the information that's being captured in the laboratory notebook and in the scientific process. So, yes.
I can interrupt for just a second, just for a bit of context. While during the break we were talking about Dr. Redfield's
Yeah.
talk, and originally this was going to be at the same time as Jean-Claude Bradley. So, just as a reminder, Rosie Redfield had talked about her work and how her department was publishing in the Public Library of Science Environmental Journals, and she was an editor in PLOS 1.
Yeah, and plus one is certainly one of my favorites. And by the way, what we're doing here, we're not doing this instead of submitting articles to traditional publishers. This is an additional process. It's an earlier process, and it contains more information than will eventually make it to the final article. But it's not an either or situation. And obviously, I favor open access journals, and so PLOS One would definitely be one of our targets. So, if we take this to the next level of openness and transparency, we have what I've been calling open notebook science. So here we make the actual lab notebook and ancillary information completely public, so anyone can access it in as close to real time as possible. So I'm going to move on to the next slide. This shows the overview of the research that I'll be discussing. So we are in the middle of this slide. Drexel University and my group, we are involved with the synthesis of organic compounds. And through open notebook science and trying to do science in a transparent way, we've actually found collaborators. That's probably the most useful outcome of this whole experiment. And we have collaborators, especially Rajarshi Guha at Indiana University. We've had some additional people, Susu Tan in Singapore, and they've basically done docking studies for us to tell us which compounds we should make to have the best chances of getting compounds that will be anti-malarial agents. So on that side, my group doesn't have any expertise in that, so we rely on people to do the calculations. Now, once we make the compounds, we don't do the testing ourselves either. We collaborate with other people, primarily, at least recently, Phil Rosenthal, UCSF. He's done testing of our compounds against malaria and against some malarial enzymes. We've also sent some compounds to Dan Zaharovitz at the National Cancer Institute, who's tested them for anti-tumor activity. So this is sort of the big picture. So when I'm going to be showing lab notebook pages and things like that, it's going to refer primarily to our synthesis part. But this is how it all fits together. All right, the next slide. I'm showing the basic Useful Chem infrastructure. Useful Chem is the name of the project. So our main objective right now is the synthesis of anti-malarial compounds. And it doesn't rely on one technology. It's actually a network of mainly free hosted technologies that include a wiki, that include a blog, that include Google Docs, and that include a mailing list. And each one of these components was added because we had to, because the other components didn't do quite as well what the additional component did. So this project sort of evolved over the past couple of years, and this is the configuration that we currently use. All right, next slide. The way that I like to talk about open notebook science from a very visceral perspective is, where's the beef? When you typically read an article, there is an experimental section to it. There is even a supplementary information section often that is freely available off of the publisher's website, and that does contain more information, but it typically does not contain all of the information contained in the original lab notebook. So it's kind of interesting that publishers do not require the submission of lab notebook pages when you publish an article, but that's not the way that it's been done traditionally. So what I'm trying to show here in this slide is I have a blog post, and I'll get to the blog in more detail later. But in this blog post, I'm making all kinds of statements. But then you'll see in red, in that red square, I'm saying see experiment 150. And that is the link to the laboratory notebook. So if someone were to click on that, they would be taken to the next page, which is a page from our wiki. And this has very much the same look and feel as you would in a paper organic chemistry lab notebook. You have a scheme here at the top, and then you have a bunch of sections. Now the page is too long to show in a PowerPoint, so I'm breaking it down into different sections. The first section is the objective, and so if somebody finds this page, they should be able to figure out why we're doing what we're doing, and follow up with various links. So I don't have time to go through every single link here, but I'll show you a few samples of the kinds of things that we can link to. So you see where it says here, the very first sentence, to synthesize a Yugi adduct from phenanthrene, etc. So I'm going to click on that link, Yugi adduct. It takes me to the next slide. It takes me actually to a ChemSpider entry. Now, is your group familiar with ChemSpider?
No, not too many chemistry majors here, I think.
Well, what I'm showing you is basically some searching techniques from the standpoint of chemistry, but they're certainly applicable to other fields. It's just that each field will have its own ways of indexing things. So sort of think of it like that. Like what's happening in chemistry is also happening in other fields, but it might use a different format. ChemSpider is basically a free website that has about 20 million molecules on it. And they enable chemists to create molecules there and to link to them. So basically, instead of managing the molecules ourselves on our server, I find it preferable to use a service like ChemSpider and have them worry about how to index the molecules and how to store the information. So what we're doing here is we are expanding our network, and we're distributing the load onto other people who are actually, expert at doing what they do.
Jean-Claude, this is Heather. I'm trying to picture what's happening. Is ChemSpider, people go in and put in descriptions of the molecules, and is it anybody? Is it kind of like a chemical Wikipedia, or?
Yeah, it's sort of like a chemical Wikipedia, although there are people who want to do that as well. This is not a Wikipedia entry in the sense that you can write anything about the molecule. Basically, this is like a database of molecules, and if the molecule exists there, then you can just simply link to it. This particular molecule didn't exist, until we made it. So once we made it, we created a new entry on ChemSpider, and you see all these different things like empirical formula, molecular weight. All of these things is automatically calculated by ChemSpider, so we don't have to worry about all that.
Cool.
All right, so I'll move on to the next slide. Okay, so here we're linking to the experimental plan. It's just a way that I like to organize things in my lab. So when we have each page will be a similar experiment run over and over again using different compounds. So we have a page here that basically gives the default procedure to follow. Okay, and again, so this is something that is not typically part of a traditional article that can be made available. All right, I'm now looking at the link to docking procedure. So here, if you remember, I was telling you about our collaborators at Indiana University, and they basically use calculations to figure out which molecules we should make based on their probability of being malaria inhibitors. So those calculations, are part of the experiment, and so we also make those available. So this is the procedure that was used by Rajarshi to rank our molecules to tell us which ones we should make. If I go to the next page, I've just clicked on a link on this page that actually takes me to the individual molecules that they calculated. So you see a bunch of C's and N's and O's. Those are basically representations of molecules. They're called smiles, and they're a different way to represent molecules besides drawing a picture. So obviously, it's much easier to handle text like this than it is to handle images. And so we use a Google Doc here to basically store the smiles information. But the only thing that you need to realize about this page is that each one of the cells is one molecule. Again, information that's not typically made available. Okay, I'm moving on to the procedure section. So again, all we're doing is we're taking a look at that original page, and we're going through all the different sections of it. So this section resembles most what you would find in a traditional organic chemistry article. It's a procedure written in sentence form. It's got characterization information. And the idea here is actually to copy and paste this when we are ready to submit to a traditional publisher that will have that much less work to do. We can just copy and paste. The next slide, link to raw data with JSpecView. So here what we're doing is...
Jean-Claude, if I can interrupt
Sure.
for a second. I'm just wondering that writing up of the procedures, so actually as you're going along, does that change or affect your processing? So I'm just thinking, what's the difference between doing this as opposed to the traditional method? Does it force you to get that procedure down in writing at an earlier stage, or in better language because it's up there in the web, or
You mean the plan procedure,
yeah,
or the one at the very end?
the procedure that you were showing at the previous slide.
The procedure section.
Yeah.
That's done after everything else is finished. Yeah, because when you first do the experiment, you don't have this information yet, and this information is actually extracted from the slide that I'm on now, the link to raw data.
Okay.
So if you see there's like a graph there and there's a bunch of numbers. So essentially what that characterization information is, it's basically typed out the values of these various peaks, more or less. Okay, so what you're looking at here in this graph This is an NMR spectrum. It's a way of analyzing the molecule. And again, this is raw information that's not made available to this extent. We make it available in a way that anyone over a browser can expand any part of this spectrum. So you see there's that little peak, there's the red arrow going to, a little peak, and then a red arrow pointing up showing the expansion. And in the expansion, you can see in much greater detail what that peak actually looks like. All right. If you look at the supplementary information section of most publishers, you will typically find PDF files, and you will not find this expansion unless the author went out of their way to do it. So this, I think, is again a very important way for other people to judge your raw data, and they have to have access to everything in order to be able to do that properly, I think. Okay, so the next slide, the conclusion is fully supported. Even if you don't necessarily follow the chemistry going on here, hopefully I'm giving you the impression that we're providing a lot of data. We're providing all of the raw data that the people from my lab are using to make conclusions. So at the very bottom of this page, it says, this product was obtained in 59% yield. Well, you don't have to take our word for it. You can actually go and reanalyze all the information yourself, and you may come up with the same conclusion, or you may come up with a different conclusion. And that's really the power of open notebook science, in my opinion, is that you keep everything out there in the open, and you can have a real discussion with people about it. They do not have to trust you. Okay, so do you guys have any questions about that part?
Any questions or comments, feedback? Is this making sense? Is that, can you hear that?
Yeah, I think that's the point that I wanted to bring across. It's not so much the chemistry as it is the concept of making all the raw data available. Exactly. So if you move on to the next slide, it's it.
Sorry, I think we're crossing here. Emma has a question.
Okay. Yes, I have a wonderful example at the very end of my presentation of something that happened this week, actually, that I'm very happy about.
Okay.
Okay?
Yep.
All right, because I'm going to move on to a different section here, indexing the experiments in Google. So what I showed you up to now is basically on the wiki how the information is stored. All right. Now the question is how do you actually find that information if you're looking for it? So what we do on every page, and this is on the wiki, it's on the blog, it's pretty much everywhere where we talk about a molecule, we put these tags. Okay. Now I showed you a tag previously that I call Smiles code. There are other tags, and unless you're in chemistry, there's not much point in discussing it except to say that there are reasons why you'd want to use other things. And some of these other representations here are called inchies and inchy keys. So these are, again, just ways of representing the molecule unambiguously. So if we put all of these tags to represent every molecule that was discussed in the experiment, Google will actually index these pretty nicely. So that if you were to search Google for an inchy key, all right, that string of characters QECI, that just represents one of the molecules that we're using, and it pulls up, as you can see, all of these different results: experiment 165, 166, 178, 161, etc. So somebody searching with that inchy key would actually find, all of the experiments where we use that molecule. The only tricky thing about using Google for this is Google will assume initially that if it finds more than one page from the same website, that you're only interested in one of the pages. In this particular case, that's not true. We want to actually see all of the experiments. So you have to click that link that Google gives you at the end to repeat the search with the omitted results included. But if you do that, Google, I think, is pretty good for this kind of indexing. All right. So a little modification on the Google searching. I figured I would talk about this because of the library. Try to focus more on the searching. So I don't know. Are your people familiar with the Google custom search?
Yes, good. Okay. Yeah.
Next slide.
Asking us questions.
That's the next slide.
Yay!
Yeah, I love the custom search. Of course, the difference is, using Google in general, people don't have to know about you. If they do know about you, then obviously if they use the custom search, you get much better quality results. So in this particular case, it's the same Inchi code run again, and you can see that it finds hits from our blog, it finds hits from the wiki, it'll find hits from a number of websites that I selected to represent useful chem. And that Google custom search is actually at the top, at the very top of the wiki to make it convenient. Okay, so next slide. So I showed you how we would search for our experiments, but how are other people finding our experiments? So the past 2 or 3 weeks, I've sort of collected interesting search examples by looking at the site meter hits on our blog and wiki. And it basically comes down to 4 major categories. So people are sometimes looking for specific compounds, and I've listed that here: phenylacetaldehyde, methanol, benzophenone, sulfuric acid. So that's kind of interesting. And again, people are mainly using the actual chemical name, not so much the Inchis and Inchi keys. So that'll be interesting to see over time how that changes. For now, this is what people are using. People are also...
Jean-Claude, this is really interesting fit with our previous speaker, because he was just talking about metadata and within institutional repositories and how do we get this working. So these beautiful examples of these are the things that in chemistry people are going to be looking for and that need to be there.
Yeah, absolutely. I think that it's very important to find out how people are finding your stuff, because that's your audience. Whatever you think your target audience is, this is the actual audience. These are the people who are finding it, and using a blog and a wiki, Google rewards you tremendously. I mean, almost all of these are in the top 10 of sometimes several million hits for these search phrases. So this is definitely a way that that Google and other search engines are rewarding you for using their services, and it's the way that people think. So knowing that people are looking for these things, I can ascertain whether or not they're finding it. And so, for example, if you look at experimental conditions, you've got things like kinetics, Bach deprotection. So you guys aren't chemists, you wouldn't necessarily know what that means, but I can tell you that that's actually something that's answered in our wiki. And so I know that the person typing that has actually found what they were looking for. And so that's not us adding metadata or anything like that. That's just taking it off what the text of our experimental descriptions. All right, I'm moving on to the next slide, which is a little bit broader. There's a lot of people searching for educational material. So, organic chemistry quiz, 3D periodic tables, things like that. So there's all kinds of educational hits. And there's also, a lot of big picture type searches, like protease and malaria, automated reactions, chemistry web 2.0. So these are pretty big concepts, right? And they go well beyond our specific project of making anti-malarial compounds. But again, it shows you, what useful chem is all about, and what people find, need it for. And these are some of the things. Okay. Next slide, using ChemSpider to archive compound characterization. So I talked about ChemSpider a little bit before, and I want to go into a little bit more detail some of the recent features that they've had. Not only can you store your compound, but on that page you can store the raw data of the spectra. You can store images. You can store 3D crystal structures. So this is called the characterization of a compound. Once you make a compound, you have to prove that you've actually got it. And it turns out that with something like ChemSpider, you can actually store all of those raw data points in there. So I'm very excited by this, and this is the direction that my lab is going to go. So this is for final results type of thing. All right, so you wouldn't store here failed experiments or things that are ambiguous. This is for the final results, the stuff that you do typically send to a journal. And again, the advantage of using something like ChemSpider is if you look at the molecule up there, you'll see there's a structure that has 3 rings in it. So you can actually say to ChemSpider, find me all the compounds that have exactly these 3 rings, and it'll do a substructure search, and it'll pull up your molecule. So somebody that doesn't know about our research will be searching ChemSpider, and they might be doing a substructure search and fall upon this compound, and now be able to use it in their research. Okay, so again, it's that scholarly communication. How does one researcher find another? Well, we're very familiar with the traditional ways, of using indexing services, chemical abstract services, and things like that. This is a free mechanism that I think is going to be used more and more, and it's very exciting.
Jean-Claude, do you have any examples of cases where you or your group have found stuff using ChemSpider, or where people might have found you?
No, I don't have an example of someone finding us through ChemSpider. Part of the reason is it's hard for me to track that because I don't have the ChemSpider logs. Although I can probably talk to them about that. That's an interesting question. I am in communication with them. They're very active in implementing new tools if it makes sense. So I can definitely talk to them about that. I mean, normally what happens here is there's a saying that data finds data. So even though I don't know exactly how somebody may have found my research, I've got a lot of stuff out there. They're doing a lot of searching. They've got a lot of stuff out there. At some point, one of our 2 branches will touch, and once that happens, it doesn't matter which one was the first branch. We'll then communicate and have a collaboration. So I showed you the site meter results because those are specific instances, right, of people finding me. But if you're asking about how efficient is it to find collaborators, that's a little bit harder to quantify. But we definitely have found several collaborators, so it does work somehow. Did that answer your question?
Okay, yeah, thanks.
You gonna say something?
Yes, that answers the question. Thank you.
Okay. All right, so I'm moving on to comparing experiments with Google Docs. So Google Docs is actually a really convenient service for freely sharing information in a table format. So, we do a lot of reactions, and those reactions are stored on web pages, right, on the wiki pages. But they're really hard to compare to each other. So another format of representing the information is to put it in a giant table. And this table is searchable by anyone. And if you're looking, for example, for all of the reactions where we got to precipitate, well, you can do that by sorting the table. You can also export Google Docs to Excel and then do whatever you want with it. So, and that's something that can't be done easily on a wiki or a blog. So this is actually really important. Okay, the next slide talks about the most important section. When you were asking me about, when do people write the procedure? Well, that's done later. The very first thing that gets recorded on a page is the log section. And the log section is date and time of what happened when. Okay, and if you're missing this section, if the students forget to record it, all right, or don't record it, the rest of the experiment is garbage. Because if you don't have the original data, you will forget when you did things, and things are going to become a mess. So I, make my students finish updating their log, by the end of that day, but they can upload the data, the characterization data later. They can upload images later. They can upload schemes later. This is the section that's absolutely critical, because you can create the rest of the experiment from the log section, but you can do nothing without the log section. But the problem with the log section is that it's written free form, right? So if you're a chemist and you read this, you can understand it. At least you should be able to understand it. But it makes it very difficult for machines to read. Okay, so if you go to the next slide, the other thing that we're doing is we are converting the log section that's written in free form, in free format, to an extremely rigid way of representing steps. Okay, so these are the workflows. And so a page here, you see it says add container, add compound, weight, add vortex. So these words that have capital letters, these are just a few of the allowed things that you can do in this particular experiment. And definitely a machine should be able to read these and convert this to a database, and basically convert it to any other format that they want to. So if we're collaborating with people, they don't have to start from our log section that only humans can read. I could just give them the dictionary of the words that we're using here, and they can translate it to whatever format that they want. Okay. And next slide, comparing results in a table. So, although you might think that the experiment is the smallest unit in science, that's not actually true. It's actually, each individual result is the smallest possible unit. So, not to spend too much time on this, but each experiment has a bunch of results, and it turns out that it can be very useful to take out each and every one of those results independently and represent them each on their own. And I think, as we talk about science becoming more automated, this is a direction that I think would be very useful and that we're going to pursue. Okay, next we have the table of contents. This is just a page on the wiki that looks like a familiar lab notebook. So if you're looking for a specific experiment, it's probably a pretty good idea to go on that page and to quickly scan through and see if you can find what you're looking for. Again, if you're looking for exhaustive reports, or if you're looking for systematic reports, you want to go to like that table I showed you from Google Docs. But if you already know the experiment number, this is probably the best way to do it. Okay, so I'm going to quickly take you through on the next few slides why it is that we do use a wiki, in fact, for the lab notebook. We didn't at first. We actually used a blog a couple of years ago when we started this, and it turned out to not work very well, because with a blog, if you change the information, there's no record that it actually got changed. But with a wiki, every single change gets recorded and there's a date timestamp put on it. So if I want to figure out what's going on in the lab, I can just go and click on the recent changes button on the wiki, and it'll tell me, experiment 158, and I can then look, into that experiment and see, what that particular student did. So this is a way of checking for all changes in the wiki. Yeah.
Wondering why that would matter.
Why it would matter what's going on in the lab?
Or why would it matter being able to have that date and timestamp?
Oh, because you have to be able to prove that you knew something when you knew it. Yeah. I mean, part of what we want to use this for is to cite precedents. So if I don't have a date timestamp, how am I going to prove that I just didn't create that page yesterday?
Okay, thank you.
Yeah, so it's going to that concept of the citation. I believe strongly that you can use different wiki versions as powerful citation tools, The only thing is, don't run your own wiki because you're going to lose credibility. I mean, that's the advantage of using something like Wikispaces that has it's a third-party date timestamp. So I have nothing to do with that. I can't change the time on it. Whereas if you're using something like, that you're running yourself, theoretically you could do whatever you wanted. Okay, next page. I'm just showing what it looks like.
Jean-Claude, I'm wondering the date timestamp on the wiki. Is this something that's currently accepted um, in academia and in chemistry?
No, but we're going to try to make that happen. That's part of the experiment of what I'm doing here is, we're going to be using these as citation tools. And look, right now in a paper, you absolutely can cite a website, right? I mean, it's done all the time. And this is just a website. So I don't anticipate any problems with that, actually. Um, okay, so real quick, the next page, tracking versions of wiki pages. So if I were to click on a specific page, I can now see all of the different versions of it. And if I move to the next slide, comparing versions of wiki pages, you can compare any two versions, and at least with Wikispaces, it's pretty nice the way that it shows you the comparison. It puts in green all the stuff that's new, and it puts in red the stuff that got deleted. So you can really track exactly who did what when very easily. All right. Next slide, telling the story of the failures. So this is another way that I really like to use the wiki. We were just talking about citations. So here I have something where we tried to make a compound called dopal, and we did get it to work at the end, but only after 25 experiments. So normally you wouldn't talk too much about the 25 experiments, but because this is not a traditional article, I can do whatever I want. So I can actually write a document that explains how we failed. And that can be very useful, I think, for other people trying to do similar experiments. Okay. Next, you have a mailing list. So the mailing list is a relatively recent addition. I tried not to use it, but it turns out that it does serve a purpose that's different from the wiki, different from the blog. It's a very convenient way to interact with people who are not in your group. So we're collaborating with various groups, and it's just easier for them to hit reply to an email than it is for them to log into our wiki. And so, we basically use that because it works. All right, so next slide, I'm going to talk about the blog, which is, the very last part of all this. Basically, the blog is used for any kind of milestones or big picture kind of discussions, right? So I'm not going to be putting detailed experiments here, but I may talk about something some interesting problem that we're having, or some kind of milestone. And I just want to very quickly give you examples. So in the past few months, these are some of the things that I've discussed on the Useful Chem blog. One of them is a funding. So when I submitted this proposal to NSF, I put it on Nature Proceedings, which I don't know, Heather, are you aware that Nature Proceedings will no longer take proposals?
No, didn't know that, and we haven't covered nature proceedings in the past.
Oh no, shame on you.
Oh, mistakes obviously.
Yeah, I think Nature Proceedings is one of the most important components to this because it gives credibility from the Nature editors to a piece of scientific documentation, and it gives a nice author list. It gives a DOI. So definitely, if you can, you should put something on Nature Proceedings. The the problem, I mean, they used to take a lot of things. I guess they're focusing more and more on results right now. But yeah, they're no longer taking proposals. So one of the things that's being discussed right now in the blogosphere is some repository for proposals. So Noam Harrell has actually been working on that, and I'm sure we'll continue to discuss it. But anyways, you can't do this anymore.
Jean-Claude, I have a question about the repository. I'm just wondering, has there been any discussion of a repository for chemistry, like we are for physics?
Well, again, now you're talking about article format, right? So you're talking about like a preprint server.
I guess you could have a repository for different types of things. Yeah, archive is a preprint server. I'm just thinking repository. It might be if you're wanting something for proposals, and chemists might be looking for something different in the repository. I'm just wondering if there's been any of that kind of discussion.
Yeah, I mean the whole proposal thing is very interesting because of course the proposal is one thing that never gets published, right? It's never supposed to be published in an article. Um, yeah, that's what we're piecing together. I mean, the reason that Noam is talking about it, and I helped him out a little bit in setting up a wiki for this, is that it doesn't exist, and so there is not one central repository that will take this. You have institutional repositories, of course, right, and you can do whatever you want at your own institution. But yeah, each one of these very specialized repositories, like for example, University of Southampton has just helped us to create a repository for crystal structures. So, but that's only good for crystal structures, okay? Because it needs its own special searching software, its own special storage software. So what's happening is there's not one central site for chemistry, but there are lots and lots of little sites that coordinate special aspects. ChemSpider would be another example of a specialized repository.
Making sense to me now.
Okay. So again, real quick, next supporting funding initiatives. I'll just step through these pretty quickly because I know we're running out of time. Highlight popular media coverage. So if useful chem gets covered, by media, I will obviously, put that in the blog. Highlight peer-reviewed coverage. So if there's a peer-reviewed article that cites useful chem or some experiment in useful chem, I want to highlight that. I want to make a big deal about that because that's where the peer-reviewed and the non-peer-reviewed literature is going to merge, and that gives credibility to both sides actually. So I definitely want to highlight that. I also use it to announce collaborators. So Gus Rosania from University of Michigan is a recent collaborator who's going to be looking at drug transport for our anti-malarial compounds. Matthias Zeller, he does the X-ray crystallography for us. So he's a relatively recent addition. Next, Phil Rosenthal. I talked about him before. He does the malaria testing of our compounds. Next, I discuss presentations in real life. So, like this talk, for example, I might, blog about it. And, if I record it, then I can give a link to the recording. I can discuss presentations in Second Life. And I think you've been to our presentations, right, Heather?
No, I haven't been to your presentation in Second Life.
No. Have you been in Second Life?
I haven't, no.
Oh, there's another topic there. You're gonna have to assign that to your students. There's actually a little party going on American Chemical Society Island tonight on Second Life. So the information's on my blog. If some of your students are interested, I'll meet them there in about 4 hours. Okay. So showcasing new science in new media, showcasing teaching in new media. So I've also used Second Life to teach my chemistry students. And here's a picture of one of my students writing on a camphor molecule. So Second Life, that's a whole other talk, but I think it shows a lot of promise for chemistry. Alerts to broader impact opportunities. So because we know we're dealing with malaria, even though I'm a research lab, I might get contacted by other groups that are malaria oriented who want me to pass on information. So having a blog is a pretty convenient way to do that. Next, science philosophy. So I've touched a little bit on some of these things. There's again the chemistry is where those are the trenches where we're operating, but I think there's a much bigger picture here. that's more general to how science actually gets done. So I will often, or sometimes post about, some science philosophy. And next we have Gus Rosania's notebook. So there are some other people who have started to do open notebook science. Gus Rosania is one of them. All of his students actually post every experiment that they do, and he's also using the same wiki model that I started here. Okay. Next is the collaboration with Brent Friesen's teaching lab. This is what I wanted to tell you about earlier. This is one of the great things that comes out of doing a project like this that you don't anticipate. Brent is at Dominican University, and he came across our useful chem site and the fact that we were making antimalarial compounds, and he got into the chemistry of the Yugi reaction. It's a specific reaction we're using to make those compounds. And he thought it might be a good idea to have his lab, his teaching lab, make more Yugi compounds. So he's actually just written the lab manual for his lab starting on Monday, and his students are going to be making molecules, and if they make any new molecules, he'll ship them over and we'll get them tested against malaria. So that's actually a pretty neat opportunity, because in a teaching lab you don't normally get to do real research, right? Typically you're repeating procedures that have been repeated for 100 years, but here his students may actually do reactions that are completely new and might lead to something useful. Okay, and next I got Cameron Nyland's notebook. So Cameron is at the University of Southampton, and he is also doing open notebook science. Although he doesn't use a wiki, he uses his own customized software, but just to show examples of other people doing this. And the last slide, where is science headed? I think that we're at a really interesting part right now, where we're going from a world where humans are trying to communicate with other humans, and that's the main idea behind publication. We're moving to a world where it's actually important to communicate with machines and to have machines communicate with us. And I showed you a little bit of that with converting our logs to a machine readable format. I think that eventually we're going to go to a world where there's going to be more and more machine-to-machine communication of actually doing new science, where machines are designing experiments, they're executing them, and they're analyzing them. And that's where I see where we are right now, is sort of going over to that model slowly but surely. And so it makes it pretty fun to be part of that whole process. But that's the ultimate big picture of what we are doing. And that's all I have.